Hello, and welcome to a presentation about the 240-hour eelgrass mapping co-op completed this summer, 2020.
So who are we? I'm the picture on the left, Camryn Roberts-Capak. I'm a junior in the class of 2022.
And that's me on the right. I'm Grace Jensen, a senior in the class of 2021 in the Marine Science Safety and Environmental Protection major at Mass Maritime.
Starting off with the organization, we work directly under Mass DEP, or the Massachusetts Department of Environmental Protection. And under Mass DEP, we have Michael McHugh. And he was the aerial interpreter, so he took the images from the flyovers from NOAA. And Thomas Greskos, he was a GIS analysis. And then starting with MMA, the MSSCP department. On this co-op, we had Professor Hubbard, and he was the principal investigator. Dr. Heffron was the assistant principal investigator, and then the students, myself, Camryn Roberts-Capak, and Grace Jensen. And then I put NOAA off to the side here. It was NOAA Center for Coastal Studies. They're the ones that did the contract flights for Mass DEP. So they were in collaboration, so I just added them off to the side. So what is eelgrass monitoring? This study began nearly 40 years ago by a single man, Costa, who hoped to observe an overall increase in eelgrass populations after the disease wipeout in the early 1900s. Mass DEP extended this study beginning in 1994, and MMA recently collaborated with Mass DEP starting last year in 2019. And they're monitoring any changes or new trends in eelgrass beds. Eelgrass serves as a biological indicator that can reflect local water quality. And we're looking for any declines in population. And this can be caused by local disturbances. The source of disturbance can be sought out and require local towns to lessen the degree of their negative impacts. So we have 4 total project areas. Last year, the first year this project began, was the South Shore and Cape Cod. South Shore of Cape Cod and Nantucket. And then this year of 2020, we did Buzzards Bay and Martha's Vineyard. Next summer, 2021, they will do Plymouth, the North Shore of Cape Cod, all the way to Provincetown. And then in 2022, they will do Plymouth all the way north to the New Hampshire border. And then in the year of 2023, Mass Maritime will repeat these project areas again.
So the first step to us getting points to survey out on the water is having a NOAA spotter plane fly over the area of study. The plane captures images, and then they are sent to Mass DEP for analysis by an aerial imagery expert. His data then goes to a GIS technician who plots the locations of eelgrass beds and specific points that need closer investigation, which is what we tackle out on the water. Eelgrass beds are marked with a bright green outline, and the points for us to investigate are placed less than 50 meters of one another. And depending on what needs to be investigated, they may be placed within the polygon or on the edges. There were times this summer where Mass DEP wanted us to confirm if the edge of the polygon was accurate or not. So what is it we're looking for? That would be Zostera marina, or commonly known as eelgrass. It is a submerged rooted marine flowering plant with wide distribution in the northern hemisphere. In terms of biotic importance, it provides sustenance for waterfowl, habitat for fisheries and shellfish. In an abiotic sense, it is a crucial component of sediment and shoreline stabilization, and it's an indicator of water quality. Availability of light is the primary vulnerability to this plant. Things like nutrient loading, phytoplankton blooms, suspended sediments, and epiphyte covering the blades of eelgrass can affect the amount of light the plant receives in order to effectively photosynthesize. Those are just some of the natural threats that this plant can face. There's also anthropogenic causes that lower eelgrass populations.
So again, some of the disturbances to eelgrass can be heavy nitrogen loading, and the causes of this can be nutrient runoff from fertilizers, leaching septic tanks, or treated wastewater runoff, and also development. So examples could be docks, mooring anchors, and boat anchors.
The internship entailed a variety of responsibilities. The primary duty was to be prepared for field work days out on the boat. We would report to the docks at 7 a.m. to launch early to beat any upcoming winds. We also had a variety of monitoring projects we attended to in the aquaculture lab. On days that we couldn't be on campus or out on the water, we worked online from home, typically editing raw video we captured from previous work days. So going into the internship, there were a number of COVID-19 safety protocols put in place. Mass Maritime Health Services carefully reviewed the work we were doing this summer and came up with the following protocols. Firstly, there was a 4-person maximum to be on board the boat at any time. It was myself, Camryn, Professor Hubbard, and Dr. Heffron. We had to maintain a 6-foot distance as much as possible and wear a face mask at all times. We were advised to use fabric masks in the event that they got wet. As we rotated workstations on the boat, we would sanitize the equipment after their use, and we also had a plastic shield installed in front of the center console to prevent particles from blowing back while traveling. Maximum distances were to be maintained when anyone was eating or drinking, and we were advised to practice social distancing when at home. In addition to our COVID-19 protocols, we also maintained typical boating safety practices, like wearing a life jacket at all times and wearing slip-resistant footwear. To keep everyone on the boat safe, we would slow down when approaching wakes or waves from passing boats. When traveling at full speed, everyone made sure to hold on to a railing or be seated.
Some of our boat responsibilities included driving, navigating, handling lines, operating the GTAC computer and ArcGIS collector, controlling the underwater camera, as Grace is doing in this photo, and as well as cleaning and maintaining any equipment. So this is the research vessel Zostera. It's a 22-foot Seahawk center console. The fiberglass hull was actually donated to Mass Maritime. And then Mass Maritime added the Suzuki 150 horsepower motor. It also is equipped with a jack plate here in this photo on the left corner. And this helped when we were in shallow waters. We could actually just raise the whole engine up. And there was several times where we had to be in shallow waters to find any points. And a few times we actually came aground and we had to use the oars to push off into slightly deeper water and then start using our engine to propel us out of there. And then the picture in the middle here, we have the SIMRAD, which is the navigation system that we used. And then these switches down here gave power to the jack plate, the navigation lights, the SIMRAD, and the screen monitors we had on board.
We had a lot of great equipment on this boat. So again, in the middle there, you can see the SIMRAD that Cam mentioned before. That was our navigation tool, chart plotter, and also it would have bathymetry readings and it would show us nautical contours so that we would know what kind of water depths we were traveling in. On the left, the yellow tube there, that is the underwater HD camera. On the right, one of our HD screens that has a feed from the camera so that you can see the footage that we're capturing. And on the bottom, that's a picture of inside the housing above the console. On the left is the GPS receiver. And on the right, that black box is where the HD video gets recorded to a USB drive.
So talking about the underwater camera, we have this swinging davit arm that we put off when we're dropping the camera, but when we're underway, we bring it back into the boat. And right here we have the pulley system, which includes the rope and the cable. And we also have the cleat lock right here on the pole, which we can lock the rope on so it's not heavy for us to constantly be holding the camera down. Talking about the laser pointers right here in this picture, we have 2 laser pointers that enhance video quality. And right up here on top of the davit arm, we have the GPS. And this gave us a very accurate location of where the footage was exactly being taken.
Operating the camera is a one-person job. When doing so, you must be mindful of lowering the camera to an appropriate depth so that it doesn't hit bottom, but also gets close enough so that we can view the seafloor. There's a small monitor for the operator to view so that they can help identify eelgrass. When commuting in between points, there were a few methods we used to secure the camera. On longer trips, we would bring it all the way into the boat and secure it. On shorter trips, we might leave it on the davit and just hold it on the gunnel of the boat, or we would secure it with a pole. It's also important to watch the lines that are connected to the camera, because if it drifts too far, you run the risk of the lines getting tangled in the propeller.
So with driving and navigating responsibilities, there's always one person driving and one person navigating at all times while traveling. For driving, we are traveling at a reasonable speed depending on conditions, usually going 24 knots max, but the boat can probably go up to 30 knots. In this picture where Grace is driving, the conditions are pretty calm, so she's probably going to about 20 to 22 knots in that picture. You have to be aware of boat traffic, lobster trap buoys, channel markers, and shallow waters. And again, slowing down for safety reasons before hitting a wake or large waves coming at us. And we're following the directions directly off the SIMRAD. And we can usually just set a GPS route, so it's pretty simple to follow the line. And we're also responsible for docking the boat. And the navigator is assisting the driver with directions and keeping an eye out for any boat traffic or oncoming situations.
So the GTAC is a rugged computer tablet that has ArcGIS collector installed on that. And that is what we record all the observed data in. And it over an internet connection, it will transmit those points directly to Mass DEP. So we use this for capturing pictures of the eelgrass from the underwater camera and recording data such as the presence or absence of eelgrass, its density if it's there, any epiphyte coverage on the blades of grass, the location within the eelgrass polygon, the presence or absence of algae and its density if it's there, as well as the depth that we're surveying and any additional observations. It was also used from time to time as a navigation tool to get to our points.
So for example, when the question asks if there's any eelgrass present, if you say yes, it asks for at what percent density. And going off this picture, less than 5%, you can clearly see only a few blades of eelgrass there. And then all the way to 75 through 100, where it's very thick and dense. And this goes for looking at the epiphyte density as well as algae density.
So in addition to our eelgrass work, we also had some projects going on in the aquaculture lab. We would maintain the tanks, feed the organisms in the tanks. We worked on a scallop study, tagged and released lobsters, cleaned and maintained the 24-hour underwater camera. It's deployed off of the docks by the aquaculture lab. You can find a link to it on Mass Maritime website. And we also would clean and calibrate a water quality sonde that is deployed off the docks as well.
For the lobster tag and release, we would initially tag the lobster and record the ID number listed, and then we would write down the gender, amount of claws, and shell disease if present. The shell disease is on a scale of 1 through 3, and 3 is the most severe. And then after doing that, if they had any bands on them, if they were in the holding tank, we make sure we remember to take those bands off, and then release them right off the dock here on the left. And at times when we pull up the lobster trap, we have lobsters that we already tagged. So essentially we can go back and look at their old data and compare to the present data and see if their disease got any worse, or if they don't have a disease anymore, it could be because they molted off their shell. And this disease can be caused by excess nutrients, just like the disturbance eelgrass with extra nitrogen loading. And right here in the bottom, this little blue thing is the tagging gun. And you have to make sure that you insert the tag inside the lobster, or because if you put it on the shell, they will molt their shell and then you'll lose the tag. And then here's just a picture of a pregnant lobster. All these black dots are the babies. So as soon as I pulled that up from the trap, I immediately released it. And you can see it's already missing a claw. So I wanted to make sure that it had a high survival rate.
So in the field, videos are recorded to a USB drive. And then we would take those USB drives home and upload the raw video files to Google Drive. Then we would take those files, which would cover transit in between points, and we would clip them so that we would just be viewing our footage of the seafloor. And then those clips would be updated or uploaded to an additional Google Drive. Professor Hubbard would recollect those USB drives to back them up again on his own computer.
And here's an example of one of our video edits. I'll play a few seconds of it. So right here you can see some eelgrass blades right there, and you can see that there's a lot of epiphytes on there. And for this area, we would say eelgrass density is about maybe 5 to 25%, and it looks relatively patchy in this area. Going to another location, you can see a lot of epiphytes on the eelgrass blades. So for epiphyte density, you'd probably say 75 to 100. Even more epiphytes.
Algae present too.
And then also we have to say what the substrate is. So this area would be sand. And other substrates include silt, so muddy areas, shell beds, or rocky. So for the NOAA scallop study, we were left over with 586 scallops from the initial study that ended last year. And we had one group of sea scallops in a lantern net that was initially grown off the dock in the marine environment. And the second group was initially grown in the lab itself. And with our experiment this summer, we were looking for any compare noticeable differences in growth. And we ended up conducting growth measurements from all 586 sea scallops, which was very time consuming. And while measuring each scallop, we measured the length, the height, and the width. And we take down any notes such as the shell having a jingle shell on top, or the shell being deformed or chipped. We'd also take out all the dead ones here and write down how many in each group. Also, these are our data sheets right here. We entered them into the computer in Google Sheets. And what we found from this experiment was the initial group that was in the marine environment were much larger than the ones initially grown in the lab. And we believe that's caused from in the actual environment, there is more of an upwelling of nutrients being received. And in the lab, in the tank, the layers towards the bottom of the lantern net were larger than the ones towards the surface. So we believe the running nutrients that were coming from the tube there was more upwell coming from the bottom, so those scallops received more nutrients. And we believe the scallops towards the surface, the water might have been warmer, and this could have stunted their growth as well. And this is a 2-year study that I'm going to complete at the end of my senior year, and I will continue to take measurements every so often. So 3 significant events that happened for me. The first one was I saw this in 2 different harbors we went to. I observed mooring fields causing direct disturbance to local eelgrass beds, and I believe that I was operating the camera at the time. And when I was looking at the bottom, I could see the mooring anchor, and then there was a circle of sand right around the anchor, and this was in an eelgrass bed. So that shows that that anchor removed eelgrass. And my question was, how can we alleviate these issues? And it was either Professor Hubbard or Grace that mentioned that modern mooring fields are now having anchors that end up floating instead of having the traditional cylinder block that is stationed on the bottom. And a second event would be the lobster diseases. Just thinking that the lobsters that we received are coming right from our backyard at Mass Maritime. And a lot of them ended up having the shell disease. So that means there's something locally in the area that is causing an excess of nutrients. And I think that's something that should be more looked into, as it also is causing a disturbance to eelgrass. And lastly, observing the high biodiversity and healthy ecosystem observed in our backyard at MMA. One day we were down at the docks and I noticed a lot of ropes were attached to cleats along the dock, and I was wondering if those were more lobster traps, and Professor Hubbard pulled one of them up, and the rope consisted of many species of tunicates, algae, seaweed, fish, crabs. It was very colorful, and it was awesome to see all that life just on one rope. And if you looked around the docks, you could see a lot of those ropes and algae and seaweed blades. And also we have the underwater camera, and every time you look at the screen, there's literally always fish swimming around. And I think that's really incredible that that's right in our backyard at Mass Maritime.
So 3 significant events for me this summer. I think the top of my list has to be from August 13th. We spent a day out in the field. We started at Woods Hole and worked our way north along Falmouth. And I got the opportunity to steer the boat for the whole day, which meant leaving the dock, navigating down to Woods Hole, navigating the shorelines, and that included maneuvering the boat over our points so that we could do our eelgrass surveys. And that ended up being a little bit trickier than I anticipated, but it was really a valuable experience. One of the things that I hope to achieve was getting boating experience. And so to have a whole day at the helm, leaving the dock, and then bringing the boat back to the dock was huge for me. I also learned and kind of reestablished something for myself doing the scallop counting and measuring. I realized that that's not something I see myself doing as a career. I would much rather be out in the field, maybe collecting the scallops or doing research on the environment that the scallops are in. For me, measuring individual scallops is not the kind of research that I would want to be doing. So I reaffirmed that I want to be out in the field, out on the water, out in the marsh, doing data collection. And then I think it was also significant that we made this co-op happen safely in the midst of a pandemic. We had a later start than anticipated because we were preparing for the safety protocols we needed to put in place on the boat, and just general school operations were kind of bracing from the impact that has hit the world. And so I was really impressed by our team pulling together and maintaining safety protocols and getting the job done this summer. It was great.
Some of my career goals going into this co-op that I hope to get out of the co-op, I want the hands-on fieldwork experience. I wanted to apply the SSCP course-related knowledge and skills that we learned in the classroom into the actual field. And I wanted to accomplish a thorough understanding of the indirect effects causing issues to not only eelgrass, but elements in the lab, such as the seal scallops and local lobster. I wanted to increase my problem-solving skills and experience in operating field equipment, and I believe those are all goals that I achieved during this co-op. And for future goals, I have another co-op that I need to do, and I hope to do this next summer, and I hope it's another co-op that was as good as this one and that furthers my experiences and passions. And for a future career, I hope to conduct research in climate change effects and or in anthropogenic caused disturbances. And I really learned from this co-op this summer that I want my career to be on the ocean. And I think I learned that I really cannot be without it. So I hope that's something I can manage in the future.
So I think Camryn and I have a lot of parallels on this front. Coming into the co-op, I wanted to have a new and unique fieldwork experience added to my resume. As I mentioned before, I wanted to get the experience boating, steering a boat, and navigating a boat. I also was excited for the opportunity to work with ArcGIS Collector. I've worked with GIS in the past, but not with Collector, so this was a great experience to have. And overall, I have to say I liked the program. Also, the opportunity to work with a state agency. Again, that's a good thing to have on your resume. And looking towards future goals, I see myself continuing to work on Cape Cod in an environmental field, doing research or conservation work. So to have experience with a state agency brings me closer to that potential. Short term, I plan to be continuing work on the research vessel. I'm going to carry on running the boat into the fall for environmental monitoring. I'll have a new team with Dr. Heffron, and we'll be perhaps finishing up some points for Mass DEP. Otherwise, we're going to be devising our own new projects. Stay tuned.
Some of the overall strengths included, number one, being able to complete this co-op during a pandemic, where most students around us had their co-ops canceled or completely moved to online, which is something that I would not want to be doing. And both of us are very local from the town of Barnstable, so the commute is less than a 30-minute drive, and this was a paid co-op working with a state agency. The schedules and hours were very flexible. This was a versatile co-op, and there was different scenery every day. This was a unique and valuable experience using underwater camera and ArcGIS Collector. Connecting and building relationships with MSSCP professors was very important to me, as Professor Hubbard and Dr. Heffron offered experienced backgrounds and immense applicable knowledge. And one thing about the team, everyone had a positive attitude and remained motivated, which made it really easy to work with everyone.
So our list of weaknesses is much shorter than our list of strengths. Getting started this summer was delayed, mostly due to COVID-19. Another speed bump was getting points from Mass DEP. Of course, that's contingent upon them getting aerial footage from NOAA. So that took time for us to get out to have something to survey. And then from time to time, we would have to cancel a boat day due to rough weather. Ideal boat days were 1 to 2 foot seas with less than 10 knot winds, and we would have foul weather cancel a day on a short notice. Because the 22-foot vessel can only handle calm conditions, really. And for the work we're doing, we want to have flat seas, having the camera overboard so we don't get too much drift with the camera and we can get good footage. And lastly, we would just like to extend gratitude and acknowledge our supervisors and the agencies that helped us get this project done First of all, Professor Hubbard, thank you so much for selecting us to be on your team this summer. This was an amazing opportunity, and I'm sure I can say for both of us that we learned a lot. And Dr. Heffron, thank you for being there as well. It was great to ask questions of you and have you teaching us everything while we were out there. Thank you to Mass DEP for working with Mass Maritime on this project so that students like us can work on this valuable research. Thank you to Mass Maritime Marine Department for outfitting the research vessel with all of the equipment we use and providing us with dock space and making sure that we're safe out there when we're on the water. And also to Mass Maritime Health Services for establishing all of our COVID-19 protocols and making sure that we would be safe out there as well.
And that's the end of our presentation, and thank you for listening.